Hello and welcome back, and today we're back to working on the Bendix G15. This is the big one. This is the one where we throw some electrons at it and see what shakes out. But first things first, what is the Bendix G15 and how did it get here? Well, the G15 is a full-fledged vacuum tube computer hailing from 1956, although this one is serial number 238. I was just looking at the frame down here for that serial number. This one's serial number 238, which means it's probably from 1958 or 1959. Still pre-1960, still fully vacuum tube computer. This thing is pretty epic. And if it does get up and start executing code, it could very well be the oldest running digital computer in North America, and that is pretty exciting. How did it get here? Well, it's on loan from Bob over at System Source Museum. System Source Museum is one of the greatest computing history museums in the world. Bob has an unbelievable collection of stuff, from Univacs to Xerox Altos to an awesome collection of IBMs and even an original Apple I. A genuine one. It's behind a glass case. But it's awesome to see that in person. So go check out System Source Museum if you're into this kind of stuff, which I hope you are if you clicked on this video, because Bob has a wonderful collection and Bob himself is just an absolute legend. So go check it out and give Bob a high five for me. And well, hopefully Bob is watching this video too, because today's a special one, Bob. It's gonna be awesome. We're gonna flip this big switch right here. That turns on the AC to this system. Now, I do want to be very clear here. We are not going to bring up the DC. The system can essentially boot in stages. You bring up the AC first, which brings up all of the filaments, so all of the vacuum tubes should light up and start warming up. It also spins up the rotating drum and all of the cooling fans. Other than that though, this system just kind of sits at that inert state, and you got to push this little green button here to get DC to start coming up. We're going to do everything up to the point of pushing this green button, because when we push this green button, a lot more things have to actually be working, and we're not there yet. But this will help us confirm some very important things. By spinning up the drum, we should be able to see if the clock track is good. So that is vital, because the heart of this machine is the rotating drum. And if the rotating drum is no good, then the entire machine is dead in the water. So today's the big one. When I said it was the big one, I meant it. It's the big one. So I want to hop over to the bench first and walk you through exactly what it is that we're going to do, what we're looking for off of the drum, and how we're going to check everything. And then we're going to come back over and we're going to flip this big switch and see what happens. Now, if you're impatient, there's timestamps below, and you can go ahead and skip ahead and check out whatever part you want. But let's hop over to the bench and get started with a little reading first, and then we'll come back on this. First things first, can we even plug it into the wall? And the short answer is no. No, we can't. If we look in the installation guide, there is this page right here, which has the power requirements. And the G15 is listed as a 115 volt machine. So that means that we can plug it in, right? Wrong. Most circuits in the US are 20 amp circuits. And if we look here, it says that the G15 needs 38 amps. However, there's a little asterisk next to it that says a 50 amp line is recommended. That's because vacuum tubes have pretty gnarly inrush current. So when we first power this thing on, I'm fully expecting this thing to pull something like 45 amps out of the wall. 45 amps on a 115 volt connection is weird. Nobody wires that up anywhere. So we had to do a little bit of rewiring of the room. We have a new socket over there, and it's all wired up for the machine. And no, I'm not going to show you how I did that, because code and regulations is different all over the world. And however you think it should have been wired up, well, excellent news. That's how we did it. So now that we have it wired up and we can plug it into the wall, what actually happens when we flip that big black switch? Well, if we take a look at this page out of the Theory of Operation manual, this is the schematic for the power supply. And we can see our AC comes in on the bottom left over here, goes through a 45 amp circuit breaker. Then it goes to the switch right there called SW9. It looks like that's the big black switch on the front. After you flip that switch, it goes a couple of different places. First thing it does is it comes straight down here, goes to the blower motor. This is that large fan that's on the bottom left side of the machine that is a blower dedicated for the rotating drum. And speaking of the rotating drum, we can see that AC also comes down here to the drum motor. So the rotating drum electric motor is powered straight directly off of AC. The AC also goes on up to the cooling fans that are in the top of the doors. There's 4 of these. So all of that is powered directly off of the AC. But the AC also has to make its way to the rest of the computer somehow. So it comes off over to the right here and goes into this insane collection of stuff. There's all sorts of madness and it's almost impossible to follow on this schematic. So instead, let's take a look at this page from, again, the Theory of Operation manual. If you look over here on the right side of the page, we have the turn on cycle timing. We can see at the far left is when the AC goes on, and then TM1 starts to rotate. Then TM1-2, TM1-6, TM1-10, then we have K1, K2, and then finally filaments are fully on. So essentially what this is doing is it starts a sequencer that I believe puts large dropper resistors in series with the filaments. And as the filaments warm up, their resistance will increase. And then the sequencer will cut out one of those big series resistors, and then it will cut out the next big series resistor and have full AC 6 volts going into the filaments. We can actually see that over here on the left with this little chart here called filament voltage application. It looks like when you switch AC on, it slowly brings the filament voltage up from a little under 1 volt to about 2 volts. And then K1 hits and we do a big leap up to about 3.5 volts where it slowly climbs again. Then K2 hits and we do a big leap again up to a full 6.3 volts. And then we get up to this big line back over here on the right called DC reset. And this is manually operated. Everything to the right of this line is involved with bringing up the DC. And you have to do that by pushing that little green button on the front. But as long as we don't push that green button, it'll come up to this point and then stay there indefinitely. And that's all we're doing today. Everything up to the point of this DC reset line. However, if we're not going to bring any DC up, what can we confirm other than that everything spins? Well, the drum has 3 read-only tracks on it. If we look at this page here, it's a little bit of information about the drum itself. We see memory consists of 21 long lines, 5 short lines, 3 short lines, 2 short lines, whatever. That's all random access memory. All of that is erased with a permanent erase magnet every rotation of the drum. However, if we look just below that, it says, in addition to the recirculating lines mentioned above, there are 3 permanently recorded non-recirculating lines known as clock track, spare clock track, and timing track. These are for timing purposes. Clock track is it says trio of signals, occurs unconditionally every pulse period. Essentially, this is just going to be a nice sine wave that creates the clock pulse that clocks the entire computer. There is a spare clock track provided. This is because if there is a fault in the machine, the read head can turn into a write head and blitz the clock track. At which point you fix the fault in the machine that accidentally erased your clock track, and you switch over to the spare clock track and have it as a backup. If we scroll down a little further, we see that the timing track, TM, is a permanently recorded track that supplies the necessary information to signify the pulse periods of every word time. Now, interestingly, it says down here, it says it is not necessary to have a spare timing track, as was the case with the clock track. A new timing track may be recorded in the field if an accidental erasure occurs. If the case arises, the procedure can be obtained from customer engineering. We don't have that procedure, so if an accidental erasure has occurred, we're boned. So we need to absolutely confirm today that the clock track, spare clock track, and timing track are all three good. But because that is a permanent magnetic recording, when that is swinging by the read head, it's actually inducing current into the read head. And with a nice oscilloscope, we can actually detect that. It's going to be on the order of millivolts, but we should be able to see it without having to apply any DC power to anything. And the reason I keep saying it's a sine wave, the reason that I know it's a sine wave is that if we look at this schematic right here, this is the clock chassis schematic, and we can see in the top left here it says signal from clock track preamplifier. But if we look in the bottom left here, it says V1 pin 3. That is the input coming into V1 straight out of the preamplifier, and it should be a nice clean sine wave. The timing track is a little different though. If we look at this page, this is a page full of all of the timing signals inside of the G15 that are coming off of the drum. And the timing track, which is TM, is visible right here on the bottom. And it's an interesting combination. It's 2 high pulses, a low pulse, a high pulse, 3 low pulses, 3 high pulses, then a bunch of lows, then 2 high, then even more lows, and then it should repeat. So we should see something that's kind of similar to that coming out of the scope. This should give us an idea of what we should see coming straight off of the drum, directly out of the read head. Now, how are we going to probe those read heads? Well, there's a big loom coming out of the drum that plugs into the preamplifier chassis. And, well, it turns out that we have the pinout for that big loom right here. If we look on PL4, that's the preamp input. Pin number 72 is red, and that is the clock. Pin number 74 is black. That's the other half of that read head for the clock. Then we have 75 for the spare clock, 77 for the other half of that spare clock, and then 68 is going to be the timing track, and 69 is going to be the other half of that timing track. So that was a lot of theory. Let's go put it to test by actually flipping that big black switch and seeing what happens. All right, moment of truth. It's time to flip the big switch here. We did take a couple of precautions. We've got a special fire extinguisher here that's meant for electrical fires. Hopefully we're not gonna need this. I have 3 cameras set up, the one I'm talking to you at now. I've got another one set up here to look at the front panel. We should be able to see the percentage of AC volts come up and the AC light come up. And I have the GoPro set up here looking at the drum. Now, if I go in and rotate the drum by hand, I can tell it is not locked, so that's good. We're not so cold in here that the heads have run to the drum. So that should spin up no problem. All that's left to do now is start flipping switches. There is one breaker on the back that we gotta flip first, so I'll walk around and grab that one. This big boy back here. Whew. All right. When we flip start here, things should start happening. Okay. Drum is spinning. Those 2 cooling fans are not spinning. The primary blower fan is not spinning. Our AC light has not come up. The AC light is glowing ever so slightly. Oh, there we go. We've got 70% AC. That is... Oh, that was the sequencer kicked off. We're a little high. There we go. We got percentage AC volts right at 100. The drum is spinning. Doesn't sound great. I don't know if that's the drum. Oh, something else clicked. We'll flip that off. I don't think that was the drum because it quit immediately as soon as I cut the power off. So if the drum was squealing like that, we would still be hearing it. Could have been the fan. The main AC fan down there and the two up there didn't kick off, but that's something. That's a start. That's a start. All right, we're gonna do a little bit of troubleshooting and then we'll flip the big switch again. All right, we had all sorts of hilarious bad noises going on. The loud squealing noise that we heard, I think was the fans, and I'm pretty sure they're all gummed up and nasty. So we're just gonna eliminate them completely. We're not running for a long time anyways. So we can do that by eliminating F16 here. That's the fuse for the main blower motor. And then F17 here is gonna be the fuse for all of the door fans. With both of those out, none of the fans should spin up, and that way we can listen to the drum carefully and hear what it sounds like. It also sounded like the drum was a little noisy, but I'm not sure if that was specifically the drum or the motor. The motor does have these little oil ports on it though, and this is something that I should have oiled when I had it all apart, and I totally forgot. So I'm gonna put a little bit of oil into these oil ports, and hopefully that quietens up the motor a bit. All right, round one went better than I was expecting, not as good as I had hoped. I think the loud squealing that we were hearing was the fans, so we've got all those disconnected. The motor has been oiled, so it should hopefully be a lot quieter. And now we have a voltmeter hooked up to the filament pins of one of the cards over here. So we should be able to see the 6-volt AC that's coming into all the filaments. And that should actually tell us how it's stepping up the voltage through the sequencer. So here goes round two. We're gonna flip this big switch one more time. The drum is spinning up. It's much quieter. That's good news. Oh, it's much quieter. That's way better. Okay, so the sequencer should be spinning. There, it clicked off once. Our AC voltage is at 2.9, 3 volts, 3.2, 3.3, 3.4 volts. There went the second click. We're a little low, that's all right, we're gonna let it sit there. We're at 5.6 volts on the AC filaments for the vacuum tubes. The drum is getting noisy again. It doesn't sound like a crash, it definitely sounds like bearings. There went a third click. We were up to 5.67 volts. Should be able to adjust this up to 100. That's 6.1 volts on the AC filaments. I can see the tubes are definitely starting to warm up. The drum is noisy, but it's not actually as noisy as the Finch drive on the Centurion was. That thing was crazy loud. So that's actually not bad. I think it's just angry bearings. The next step is to try and see if we've got a good read clock coming out of the drum. So we're gonna have to pull out the scope and hook that up. All right, this is the big one. The drum is still a little noisy, but it's definitely bearing noise because it goes away sometimes. But we have a little resistor across the two pins that we need to check. So I'm just gonna plug the scope probe into the one that should be the clock here. And we should be seeing something here. Oh, look at that. Check it out. Yes. That is a clean clock sine wave coming off of the drum. That is not coming from anywhere else. If I disconnect this, it goes away. We are reading the clock track off of the drum successfully. That's excellent news. All right, we've got one more clock track to check. This is the spare clock track. If we just hook it up here. There we go. That is a good spare clock track. It looks like we're right at 106 kilohertz, so that's further evidence that this machine is going to be running at 100 kilohertz plus. The calculations that I did said it should be at 108 kilohertz, but whatever, this is close enough. I think that's pretty good. The amplitude is real low, looks like about 250 millivolts peak to peak. That's to be expected. We don't have any preamplifiers or anything going off. That's just the magnetic flux swinging past the core and inducing a current in that winding around the core. The fact that we can see it so cleanly is epic. We have one more to test, and that is the timing track. All right, this is our last track that we need to check. This one is vital. It's the timing track. Also, the bearings on the drum seem to have gotten a little quiet. Maybe they finally got some heat in them and loosened up the grease in there and they started to smooth out. So the drum sounds fantastic right now. But this is quite important. This timing track needs to be good. And that looks like what we're supposed to see. It's going to be an irregular track. We're having a hard time grabbing the trigger on it, but that is pretty much what I was expecting the timing track to look like based upon what we were looking at in the manual. We've got, you can see 2 pulses here, 3 pulses here. That's kind of lining up with what we were expecting to see. What this means is that this drum has good clock and good timing. So that's awesome news. That is excellent news. All right, what just happened? Because mind blown, that was awesome. We just confirmed that this rotating drum has a good clock and a good timing track on it. Those are read-only tracks. Those are absolutely vital, and they are good. This machine has a heartbeat. It is pretty much alive. It is nowhere near close enough to bringing up DC and executing code, but oh man, we are definitely on the right path. Now, it wasn't all puppies and rainbows today. We have a lot of problems, and they're all bearing related. The rotating drum is grumbly and squealy, and sometimes fine, and then back to being grumbly. We need something to kind of loosen that grease up and distribute it fully across the bearing to kind of revive that bearing. Unfortunately, the bearings are sealed bearings, and you're supposed to just replace them. But if we remove them, we blitz our alignment, and I wouldn't know where to get replacement bearings that are in good shape anyways. So we got to find a way to revive those bearings in situ. But while we're working on the bearings for that, we also need to work on the bearings for the cooling fans. So all 5 of the cooling fans are going to have to come out, come apart, and get cleaned and re-greased, and hopefully when they go back in, they'll spin up no problem. That will essentially mean that everything up to the point of bringing DC up is working perfectly. But bringing DC up is another massive hurdle that we're going to get into next year. To bring the DC up, all you really got to do is just push this green button. And if I had pushed that green button today, the sequencers would have started and would have attempted to bring DC up, but that would not have been smart. There's some things that we got to double check. The first is that there are some rectifier diodes in here. I do not think they are selenium, but we should probably check the voltage drop across them anyways to make sure that they're not dying. Also, the capacitors. There's a huge bank of Sprague capacitors, and these are probably all totally fine. They just need a little bit of voltage in them to wake them up. But we're going to pull them out and properly reform them anyways, just to be on the safe side. And we'll also check to see if any one of them is shorted. After that, once the high voltage comes up, it's going to try and start loading in the number track and writing it to the drum. Now that means that the paper tape up here has to be fully working because the sequencer automatically engages this and starts loading the number track from that. And it is in rough shape. So this whole sled is going to have to come out, and we're going to have to do a whole lot of restoration work to bring this paper tape back up and working correctly. Fortunately, I think we can do most of the testing for this on the bench, so that way when we slide it back in and we actually do bring the DC up, it should be working. The last big hurdle is that I think there is a DC lockout in the typewriter. So we have to get the typewriter plugged into the back of the machine and fully working. Now the typewriter that we got is this hilarious 28-inch platen IBM monstrosity. It's awesome. It's fantastic. But it is in a little rough shape. So we're going to have to take it apart, make sure that all of the electronics on the inside are fine, as well as make sure that all the mechanical parts of just being a typewriter are fine as well. But I think if we get all of that working, we should be able to bring the DC up and then really start troubleshooting and seeing if we have bad logic cards, seeing if it's loading stuff properly onto the drum, and hopefully start executing code. So that is kind of our roadmap for the future. I am extremely excited about this project. It's you guys are seeing this, right? You're seeing a Bendix G15 coming to life, right? I'm not going crazy. I'm not in a dream state, right? This is real life. This is awesome. How cool is this? Best Christmas present ever. I want to thank Bob so much for letting me borrow this and work on it. If you guys are unfamiliar with System Source, go check them out immediately. Bob is an absolute legend, and oh man, this is so awesome. So I want to thank you all so much for watching, and I want to wish you a Merry Christmas, and I hope to see you in the next episode.